So you are given n task level from 0 to n minus 1, which is represented as 2D array, and the task is this is known as task. Okay. So task of I is equal to enqueue time and the processing I. It means that the ith task will be available to process at enqueue time and will take processing time to finish processing. Okay. So it is saying some statement is given. You have a single threaded CPU and can process at most one task at a time and will act in the following way. If the CPU is idle, there are no available tasks to process. The CPU remains idle. If the CPU is idle and there are available tasks, the CPU will choose the one shortest processing time. If multiple tasks have the same shortest processing time, right? So it will choose the task with the smallest index. Okay. Once a task is started, the CPU will process the entire task without stopping. So the CPU can finish a task, then start a new instant, and then we have to return the order in which the CPU will process the task. Okay, so let's understand this one. Okay, give me a pen and then yeah. Okay, this one. Okay, so this is example first we have given here. So in the example first, it is saying that what we have here task, right? We have task, and task is given 1 2 2 4 3 2 4 1, and input output, this is the input task given. So the event go, how it will go. So this is the explanation saying that at time 1 task 0 is available to process, the available task is 0. So also at time 1 the idle start processing task is 0, so available task is nothing. Then time 2 available task is 1, right? And the available task is we will put into 1, and similarly we'll put at the time 3 the available task is what, 1 2, right? At time 3 it will be like that, and so on it is giving. Okay, so let's understand why we are choosing like this. Okay, okay, a minute. Yeah, so example 2 you understood. Okay, so here I'm going to show you some overview. Okay, so what the problem is saying, right? So this, you can see the map here, right? Process and processing time, right? So this is the task for available task for CPU. So the problem statement asks us to create a schedule policy that the prioritize the shortest available task, right? Means this problem asks us to create a scheduling policy, right? And that will prioritize the shortest available task. So this is known as what? Shortest job first, right? This is called shortest job first, right? This is called shortest job first. In short, you know that SJF, you can say that, right? SJF CPU, correct? Scheduling. SJF CPU scheduling is, right? You can say that. So shortest job first, SJF, that is known as CPU scheduling, right? So in this SJF CPU scheduling, right? If the CPU is idle, there are available tasks, right? The CPU will choose one with the shortest processing time, right? So there will be some processing time, right? Like this it is given, right? So if the CPU is idle, there are available tasks. So the CPU will choose the one with the shortest processing time, like this. This is the shortest processing time, right? And if the multiple tasks have the same processing time, same shortest processing time, right? So it will choose with the smallest index. It will check the index of this one. So if this is the index is 0 and this is the index of what, 3, you can say. So it will choose then this one. If this is not 21, it is same as 2, then it will choose this index. Okay, this is the you can say two concepts are there, right? First it will check the shortest if there is only one, but if there is multiple tasks have the shortest processing time, so it will choose based on the index, right? Based on the index. Now if it will choose the task with the smallest index, right, the task which arrived first, right, which task will come first. Once the CPU starts to execute a task, it will process the entire task without stopping, right? And it is nothing but what? It is non-primitive, right? Non-primitive. So you can see here we have a available task for CPU. The process, multiple processes are here. Process 1, process 2, process 3, process 4, and these are their what? Processing time. These are their processing time. So these are available tasks for CPU. So if we'll talk about order of execution by CPU, the shortest job first schedule, right? What we'll do? We'll first check with the processing time. What is the processing time, right? So first, which one will come? This P4 will come because it has a 2 processing time, right? Right. So P4 will come first, right, in the array. Next, if you'll see that processing time next is what? This time, this one, P3, right? And sorry, P2 because it is 3, right? This is 3, not 6. So it will come what? P2. Similarly, it will come 3, P3. Now it will come P3. And the last, it is as 21, so it will come P1. So if we'll talk about the time, right? Time it is taking what? 2. Now for P2 it is 3. So now we have to add the time. What is the time now? 2 plus 3 is now 5 here. Okay. Next time, P3 what have the time? 6 have, right? So 5 plus 6 is what? 11, correct? Next P1 will come, that time 11 plus 21 is what? 32. Like this it will uh, make the order of what we can say, order of execution, right? And this should be returned as the output, correct? So let's understand some more examples overview, right? And this is the thing that I have already noted. Okay, you can pause this and you can read it. Okay, next it is saying what approaches we can go through, right? We have the shortest minimum heap, right? So some times are they given, task given, sorted task given, right? So let's understand. So here the CPU can only pick a task for execution after it is enqueued, right? And thus we need to keep track of current time to see which tasks are available for the CPU and sort the tasks in increasing order of their enqueue time, right? We have task, right? What we have? We have task here. What we have? We have task here, correct? We have task here and we have enqueue time and processing, right? This is enqueue time. This is processing time, right? Enqueue and processing time. Okay, and so on we have here, like that. So now what we have to do? Now we can create a list of tasks, right? After sorting the task, right? Now we can create a list of tasks available at the current time. Available at the current time, and that we can say task whose enqueue time is less than or equal to the current time. So from the list, what we can do? We will select the task with the shortest processing time, and so we can think of sorting all the available tasks in increasing order with the processing time. We can take like increasing order, correct? We can take. Okay, so from the list we will select the task with the shortest processing time, and so we think sorting all the available tasks increasing order of their processing time. And then after selecting the task, the CPU will run that task until it is complete, and the current time will increase by the processing time by selected task. So after increasing current time, some more task might become available for the execution. So we would then add their task to order list, and again we'll sort the list in increasing order of the processing time, right? So this approach will work, but sorting our available task list every time we will update it by by cost, right? By some cost, right? It will be costly in terms of runtime. So thus it will give us a hint of using a min heap, correct? We will use a min heap. That concept come here, min heap, right? So because this gives us a hint of using a min heap data structure. So what you can do, if you are new with the data structure, right? Heap data structure, you can search the heap data structure. Okay, you will see the min heap data structure like that. We will see that. So what is min heap? What is min heap, right? So min heap is a tree data structure that always store minimum value element at the top using some comparison, like we have processing time here, or a task in index in case of ties, right? So we where insert and removal of the task are logarithmic time. Okay, so what we will do, we will use min heap and will retrieve us from the repeated sorting of list. Okay, since we can insert new task and retrieve the shortest task from the heap, correct? We will do that, right? And logarithmic time. Okay, so what we will do, the flow of our approach is something like, we will insert, what we will do, we will insert all the currently available tasks in the min heap. We will add here, okay, all the uh, currently available tasks in the min heap. Okay, and then we will pick the task with the shortest processing time, and then we will pick the shortest time, and then increase the current time by processing time of selected task, right? So what we will do now, one point we have to note that, what let's say that current time is 0, right? We will take current time as a 0. Okay, and the heap is empty. Heap is empty, correct? And so the next task is, we will enqueue at some value. Some value we will take 10, 20 will take. Okay, so the CPU will sit idle until current time reaches 10. So instead of increasing current time by 1, increasing time by plus 1, right? We will update by directly 10. Okay, which will reduce the number of iteration in our approach and will improve the runtime. So let's understand how I'm telling, right? So if we'll talk about, this is the task we have, right? If we have task 1 2 2 4 10 1 9 2 and so on, right? So this is our current time, right? After the sorting of this one, after sorting, this is our sorted task, right? So now it will, 1 you have, 2 have, this is not 10 here, right? We have swept now. So now 9 will come here, right? And then 10, then 11, and then 12, right? We have swept. After sorting, this position will get changed, right? Then minimum current task is what? 0 we are taking, task index we are taking 0, answer don't have anything, we are empty. So minimum is empty and no tasks are available for the CPU. Okay, what I am saying, minimum heap is empty and no task available for CPU, and current time is less than what? Enqueue time. Current time 0, enqueue time less than 1. So minimum heap is empty, no tasks are available for the CPU, and then we can say current time is less than enqueue time. So we have to update our current time by 1, right? Next time, what happened? Current time we have updated, right? So this is 1, right? Current time we have updated, right? And then this will come to here, right? So what we'll do, we will push all the tasks in queue time less than equal to what? 1, and into the min heap. So what we have to push? We have to push this one, right? So we are going to push into the min heap here. We'll push that, and the increment task index is what? By 1. We have to increase the task index here by 1. Okay, and so it will be look like here. So we have moved from here to what? Here. Now current time is 1, task index is 1, right? So, and one top element here arrive as 20, correct? So only one task is in the min heap we have, correct? That is this one. Now if we'll talk about the next, right, from here, right? So what is happening? We have inserted here, correct? Now we will pop the element task with minimum processing time from the min heap, but we have only one here, right? So we will increase the current time by time required to process the task, right? And then we will push the index of the task into the answer here, right? How? Like this we will do that. So next time what will happen, we will push all the tasks with the enqueue time less than 3 and then into the min heap, and then we will have to increase task by 1. So what we will have to do, we have to push the what 4 and 1, this one 4 and 1 we have to push into the min heap, right? So we have inserted. Now we have to pop the top element, right? We have to pop the top element, this one, and then because this is the task with minimum processing, right, from the min heap. Then we have to add the processing time of the current time, we have to update it, right, by 1, and then push index of the task into the current, right? Then we have to push here. Okay, sorry. Next what happened, this is updated, current time is 7, task index 2, answer is what 0 1. Now both indexes came here 0 and 1. Now what happened, we have updated these three, right? Current time, task index, and answer index 0 and 1. The min heap is empty and no tasks are available for the current CPU, right? So we will check if current time, that is 7, is less than enqueue time, that is 9, right? So we will check with this one. Now we have to update the current time, correct? So current time is now updated with 9 because that is less than 7 is less than 9. So we have to update that, right? Similarly, task is remains same, this one remains same. Now we have to push 2 3, this 2 3 where into the min heap, right? And then we have to increase the task. Okay, so let's see. Now you can see that we have updated the min heap by pushing 2 and 3, that is processing time 2 and index time 3 we have updated. Answer is still remains same. Now we will pop the top element, and then we will add the processing time to the current task, right? And then we will push the task into the answer, right? So what we have did, we have updated up current time, task we have incremented, and then we will push what one already I have added. So now 0 1 3 will remain. Now we have to push all the time which is less than equal to 11 into the min heap, and then we will push 1 2 into the min heap, and we have to increment by 1, that we have did here. We have added top element of the min heap is 1 2. Now its current time is what 11, task now we have 4, and similarly we have to push again the min heap right here which is less than equal to 11 into the min heap, and then we will push the min heap on min heap to 4, right? And then we have to increment the task. So this process will go on by updating the current time and the uh, and the uh, the array, right? So finally it will look like we have the order now like that. So the order in which the tasks are performed is 0 1 3 2 4, right? So this is the answer we'll have, and then we will return that. Now if we'll talk about the algorithm, right? If you have any doubt there, please let me know. Now we have to initialize some data structure, right, for the algorithm, right? So the data structure we have to initialize as next task, sorted task, and task processing order. So next tasks will be used for min heap to store the task with the minimum processing time onto the heap. Sorted task we will use to array to store the tasks in the sorted order on the basis of their enqueue time, and the task processing order we will use to array to store the order in which the CPU will process the task. Then we will come to the step 2, in which we will add all the tasks with their index to sort task and sort the array using the built-in order built-in function. Then we will initialize current time to 0, and while there are tasks in the sorted task, we will these are the tasks in the sorted task that have not been added to the minimum heap, or there are tasks remaining in the minimum heap. So what we will do, we will check if the minimum is empty, then we will enqueue the time of the next task is greater than the current time, and so if then we will update the current time to the task enqueue time. So next we will do insert all the available tasks, and then we will put into the min heap, and if we will pick the task on the top of the min heap, we will increment current time by processing the time, and then we will add into the task processing order, right? And finally we know that we will return the processing order, right? So what the things, first we will initialize next task, sorted task, then processing order. After that we will add all the tasks to the sorted task, and then we will sort the array using the built-in sorter function, any function we will use. Next we will initialize the current time to 0, and while there are tasks in the sorted task, right, till that is not empty, right, what we will do, we'll add we will move to all the tasks, right, and we will do some updation, right, in the other in the bit. First we'll check the min heap is empty, right. What we will put, we will check the greater task, right, from the current time, and we will insert all the tasks, and then we will pick, and then we'll do that. Finally we'll come to here. As you can see that what we have priority key. We have taken first priority key, right. Why we have taken the priority key here? Because this is our work as a next task, right. This will be our next task, and so we have to sort based on the min task, right, processing time or min task, based on what, min task processing, and then we have to store enqueue time and processing time, right. So we have to take the priority queue, then we will take like A, B, right, like that. We have to do sorting, inbuilt functionality of the sorting we have to make it. Then int sorted task, we have to use the task length we have to use, right. This is the input we have, right. So we have to take task dot length, and then we'll make a loop here, right, for all the tasks, right. Then we will take sorted task I0, and we will update from I0, right, and then I and 1, then we will use task of I and 1, and then sorted task is what, I of 2, and then that is I. Like that we have to update our sorted task, right. And then what we have to do, we have to use array.sort, in which we will pass what, sorted task, and then AV. It will compare the value, and it will sort all the sorted task, right. Then we will take a task processing order, and this is the same as the length. So now almost all the initialization we have done here, right. Now we will take initialization for current step 2. We will use this one. This is our step 1, right. Now we are at step 2. Now we have to update current time, task index, or answer index 0, right. Now we'll come to this what we can say, step 3, and then we will update what we will use. We have initialized, right, initialize current time to 0, task index 0, and this. So after that we will come to step 3, this one, and here while there are tasks in the sorted task array that have not been added to the min heap, there are tasks remaining in the min heap, right. So what we will do, we will check if the minimum is empty if the enqueue time of the next task is greater than the current time. So if so, what we will do, then we will update the current time to the next task in queue, right? So what we see, first we are checking here, right? We are checking here if that is empty. If this is empty, right, then we will check current time is less than sorted task, right? If that the case, we will update the current time. If current time is less than the sorted task, right, index at 0, then we will update this one, right? And then what we have to do, we have to update the next task, right? Insert all the tasks here, insert all the tasks here. Those tasks enqueueTime is less than or equal to current time, right? And then we have to pick up the topmost minimum heap, increment the current time by its processing time, and then we will add it into the task processing time, right? So we'll pick the top element here, right? We have to pick the task on the top of the min heap, and then we have to increment, right? So what we will do, we'll take the index next task pick 2, then we will remove next task that remove, then we will update the current time by its processing time, right? We have updating here, and then what we will do, we will add its next index we are updating, right? Next we are adding its index to the task processing order, right? And then if that is done, this loop is done, means the 4 is done, the fourth is done, right? The first previously was here to here, then we have did sorting, right? This was sorting, we used to do sorting here too. This was third, this was our 4, and this is our 5th step, okay? Because we have this sorting also here, and then finally we will return the 5. This is our complete 4th step, and this is our 5. Okay, let me explain again. We have to summarize once again, right? Yeah, see what we are doing here. First we will first what we have to do, we have to take we have to initialize some data structure, right? So we have to initialize data structure like what, next task we will do, then we have to sort a task, right, and the task processing, right? So we have taken next task, that is to min heap to store the task with the minimum processing time onto the heap, onto the top, right? And then we will do sorted task we will take, and sorted task is will use to array to store the task into the sorted order on the basis of their enqueueTime, right? Then we will take the processing time, right? We will take a task processing order, and this array is to store the order in which the CPU will process the task. Then in step 2 we will update our current time is equal to what, 0, right? So after sorting, this is our step 1, in which we will take priority, next task, sorted task, and task processing order. 3 things we will take, and this is the sorting we have to do sorting, right? And the sorting will do the step 2, right? Coming to line number 14, the current time equal to 0, that we initialize current time to 0, that is our step 3. Next, what we will do, we will come to while loop, right? We will come to while loop, and then while there are tasks in the sorted order, while there is a task in the sorted order task, right, sorted order task, right, what we will do, we have not been added the min heap, and there are tasks remaining to the min heap, right? So we will check if the, what we will check, will check if the min is empty, right? So next task dot is simply will check, right? And then if the enqueue time of the next task is greater than current time, right? So first what we will do, we will update the current time, right? If that is not the case, right? Current time, if the enqueue time, this is our enqueue time, right? Enqueue time is greater than current time, so then we will update the current time. We will update the current time. Here we are updating, and then we will the next task will be enqueue, and then we will insert all the available tasks, right? We will update all the available tasks on the next task, right? How? We'll pick the task on the top of the min heap, and then we will increment the current time, right? And then finally, see, next task of pick we will do, and we'll pick the task on the top of the min heap, right? And this is our processing time. Similarly, we'll do what? We'll do for its we will remove from the next task, then we will update our current time by processing, and then finally the processing is updated, right? Then we will return the processing task order. Next, if we'll talk about the complexity, right? So n is the number of tasks, so time complexity will be what? O of n log n, and then the space complexity O of n. So why we are taking time complexity is O n log n, right? Because see, time complexity, we have created one sorted task, right? Which is a deep copy of task array, and that is taking what? O of n, right? O of n, and we are doing sorting the task array, and that sorting will take n log n time, correct? So we will push and pop task once in the min heap, and both operation will take O log n, correct? O log n, and for each time, thus it will take n log n time in its total. How? O of n plus n log n plus n log n, and that is equal to what? Give me 1 minute. So I was saying for this one, right? We have to do what? We have to do sum, right? That we have on when we create the sorted task, and which is a deep copy of task array, right? That is come of n time it will take. Then we have what? We are doing sorted task, we have to do sorting, right? And that will take what? O of n log n, correct? And we use to push and pop the each task once its minimum heap, and both operation takes what? O of log n for that one. And if we and what for it will takes O log n, right? Time for each element, so it will take total what? N log n saying, right? So if we'll calculate this one, then what happen? We have n plus n log n and plus n log n. This is for one element, so n element is what? This one. So if we'll talk about this summation, which is equal to what? O n log n, right? This is the time complexity, and the space complexity remain of n, because we are taking one array to store all the n task, and that is our sorted task, right? Sorted task array, right? We are taking, and the min heap will also remain at the n task, right? So if we'll talk about plus min heap, right? Sorry, min heap, then it will be what? O n plus n, and that is what? O of n, right? So this is the extra space we are taking. Thank you guys. If you have any doubt, please ping me in the comment box. Thank you so much.